Today we have the pleasure of welcoming David Aulicino from Brooklyn College, who's going to tell us about trajectories on Platonic solids.
Okay, so I'd like to thank the organizers for inviting me to speak here. It's my first time in Newark, so it's a pleasure to be here. And yeah, so I'm going to be talking about trajectories on the Platonic solids. And this is a talk that very heavily on translation surfaces. And I think something I like about this, so I guess first I should say this is joint work with Jai Devathreya and Pat Hooper. Yeah, so one thing that I'm liking about giving this talk is that if you go to a talk on translation services by me or anyone else, most often they start with this motivation of rational billiards. And here, the motivation of what we're looking at is as low level as rational billiards that there's no reason to start with that. So we're going to just start with the objects that we're talking about, which hopefully are familiar to everyone, which are the Platonic solids. So just to recall them, because I didn't, when I started this project, I had forgotten exactly what there were. So the faces are regular polygons, and vertices are transitive, and so here they are. And if you want, I was able to pull this off of the internet. Where is it? Yeah, so here's the tetrahedron rotating around. Here's the octahedron, the cube, icosahedron made up of 20 triangles, and finally the dodecahedron, which is different for this talk than the others, and this is something that we're going to focus a lot of time on. So let's go back to the talk, and let's see. Okay, so one thing that's going to be very instrumental here is something called the net of a polyhedron. And so starting with those solids, you could do the following. If they're hollow balls, just cut them along faces until you can finally lay them flat on a table. And that's called the net. I'll show, it's great when you're talking about things that are so well studied because there's so many animations of this available online. So here's the net of a cube being folded into a cube, the net of an icosahedron being folded into an icosahedron. And so actually we want to do the reverse process where the net is going to be better for us than the solid for reasons that we'll see on the next slide. And finally the dodecahedron. Here's the net being folded into the dodecahedron.
So net is like one part of the one skeleton?
Yeah, so basically it's just a two-dimensional representation of it because we're still going to imagine that all of the glowings are there. So you can draw this thing exactly like that and then say, well, this is identified to that. And so we aren't going to be considering these things as three manifolds, but as two manifolds. Okay, so that's the net. And so now let me mention, go towards a new question. So imagine we're walking on the surface of one of these solids. And that's perspective I want to look at. So within each face, it's clear that there's a straight line trajectory. So now we need to figure out, well, what does it mean if we pass over an edge? Well, that's not a complicating factor because once we're in the net, it's clear what a straight line is going through that edge. And if you want to do this on, actually in 3 dimensions, you could just imagine here's a corner, take a piece of paper, fold it over the edge. The unique direction it goes in is the direction that your trajectory is going in. So this actually isn't as new as I thought. One thing I should say first, though, is that it cannot be extended through a vertex. So the point is that at a vertex, you have a deficiency of 2 pi, and so therefore, there's no canonical way of going straight through there. So that's going to be the only obstacle to this, but there are only finitely many vertices. So this is a famous, well, at least in the theory of translation surfaces, a famous paper of Fox and Kirshner from the 30s, where they actually did exactly this. And it's funny because you start reading this, and I mean, of course, the language has changed a lot since then. They apparently weren't the first to look at this long German word here, Überlagerungsfläche, which means covering surface. I'm going to hopefully give a much gentler explanation of what that is in this context. But all of these things were sort of already considered there. We are going to consider, though, a question that was only asked in a paper of Fuchs and Fuchs in, I forget exactly the year, but I want to say it was definitely this century, not in the 30s. Okay, so yeah, that's what we need to know there. So here's a new question. While we can't continue a trajectory through a vertex, we can start at a vertex, and if we're given a tangent vector, we can just consider the trajectory coming out of that vertex with that tangent vector. And so consider that straight line trajectory, and the question is the following. Starting at that vertex, can I come back to that vertex without hitting another vertex first? Okay, so hopefully that makes perfect sense to everyone. And so, well, this was already answered for the tetrahedron. The answer is no. That was a result of Davis, Dodds, Traub, and Yang, and then independently Fuchs later gave a different proof. And you should step back and think about this for a second, because to some extent this is surprising, right? Because here we have a vertex on our tetrahedron, and there's an infinite number of trajectories of tangent vectors that we could possibly go in. And we're saying that no matter what you do, you have to hit either one of the three other vertices or just start wrapping around this thing and never come back. So, okay, the answer to that is no. What about the octahedron? No. So Fuchs proved that. And then Dimitri Fuchs. And then for the cube, Davis, Dodds, Traub, and Yang, they proved that you can't do it. And Fuchs did the same thing.
So when is this? This Fuchs, for example.
So that I want to say was the Davis, Dodds, Traub, and Yang. That was maybe within the last 5 years. The Fuchs paper came out in 2016 or so yeah, very recent. And the icosahedron, again, no. Well, that leaves one more Platonic solid, which is the dodecahedron. And surprisingly, Jayadeva and I found that there is a trajectory, and that's it. You can do it. And the proof of this is, here's a net. Here is, you can draw a net in many different ways. Here's one of the nets of the dodecahedron, cut, fold, and glue. So I will pass this around because I did exactly that for you. So you can see this trajectory actually winding around, and there's one vertex that it's starting at, and it glued right back up to where it started.
You said you can't extend a line through a vertex?
Well, not uniquely, right? I mean, you can just take some other tangent vector and go, or, yeah, I mean.
So like some of these, you see some of these, you could draw a straight line through a vertex there while staying inside your net. Right? So, I mean, you mean like right here, next to it, or? No, like,
I mean, yeah, go ahead.
If I draw a straight line like this,
yeah,
this should be the way to extend it, right? If you write like this.
Yeah, if you say, well, maybe one side has angle pi, sure. But then the other side, though, because this is glued to this, that doesn't have angle pi. So, yeah, I mean, you're making a choice there. I mean, that is a natural choice, but yeah, I mean, there is a choice being made, though. Whereas if you say, straight line in the plane, then there's no choice once you say straight line. But yeah, I mean, yeah, you absolutely could do that. And there's other places where that ends up actually being somewhat significant. But yeah.
You're saying there's several choices, and they're all, length minimizing near the vertex?
Length minimizing in what?
Like if, you measure the length of a straight line as the sum of the line segments if it goes over several faces. So if you take any 2 points on the line has to be the shortest path between 2 points.
Right, so sometimes, depending on where those 2 points are, you could imagine that maybe the shortest one is going through that vertex, but there might be other shortcuts.
If it's not the case, if it's not true that if you take a straight line that goes through a vertex, then there's a unique way to extend it so that it's still locally length minimizing.
I think you cannot make it locally minimizing.
Okay.
I think you can always cut off the angle. It's like concentrated positive curvature. I'm not sure if it was that.
Yeah, because I mean, I'm just thinking even over here, maybe for these 2 points, the shortest way, is to go here. But then as you take the 2 points you're trying to length minimize, as they go up, then once you get over here, it's going to be much faster to go here and then just jump across for free because these are identified to here and then go.
Right.
So there's some, bifurcation occurring right when you hit that vertex in this. Yeah, sure. Okay, so as much as I would like to say, we just sat down one day, drew a net, and got really lucky and drew this trajectory, there's a much bigger story going on behind here, which is what I would like to present. Yeah, it wasn't a coincidence that, that we got this. Okay, so let's go back to that paper of Fox and Kirshner, and this is a well-known procedure if you study rational billiards called unfolding, which is the following. Let P be a polyhedron, and specifically want to assume that all the vertex angles of the polyhedron are a rational number times pi. And then we consider the net of the polyhedron. So I just drew a picture of this here. So here's a net of the octahedron. And now what I want to do is consider a trajectory on P. Rather, if I wanted to glue this together into an octahedron, I would glue this side to this side, because that's how it would be folded together. However, what I'm going to do instead is I'm going to rotate this 3 times by 2 pi over 3. So here, I rotate it down here, rotate this up, again by 2 pi over 3, and then it comes back to where it started. And now, instead of gluing this side to this, I'm going to glue this to the rotated copy of this, which now is parallel to it. And that's great because here where the trajectory on my octahedron was changing angle, now it remains going in a straight line. And by doing this unfolding, everything stays parallel. So you need to work out exactly what the unfoldings are, but it's really just that procedure where, if this is glued to this, find the copy of this that's parallel to this. And there's a unique one for that. And yeah, as I said, so glue parallel edges, even though parallel isn't obvious. There's many choices, but there's only one right choice. So let's return to the tetrahedron now that we have this unfolding picture. And actually that unfolding picture is exactly this Überlegungsfläche of Fox and Kirshner, that it was exactly that procedure, but you have to do a lot of thinking and translating of their language to decipher that it really is the same thing. Okay, so unfolding the tetrahedron is going to yield a torus. That's the first claim. So how do we see this? Here's the tetrahedron. This is one way of unfolding it. This side is just glued around to this. This is glued to this, and these are glued together. And that actually I don't know what net of a tetrahedron you're used to looking at, but this does work. And so for this, we want to rotate it by pi. Because instead of gluing this to this, because they're glued like this, we want to glue this to something parallel with the same orientation. So here we have 2 copies. It's not, as clear that this one's this rotated by pi because we're dealing with a parallelogram. But now instead of gluing this to this, the rotated copy of this lies down here. So this is going to be glued to this to this, and indeed we're going to get this with opposite sides glued. Well, just use a 2 by 2 matrix I mean, you can work out what A, B, and S are, and get that you can transform this into a square. Okay. So now, why is it okay to do that? Well, we're studying trajectories on each of these things, but here our trajectories have been straightened out to straight lines, and therefore it actually is harmless to multiply by a matrix because straight lines go to straight lines. And so everything is preserved in the square picture, which I like squares sort of much better. Everything works out nicely. And notice that the corners of the tetrahedron, or the vertices of the tetrahedron, lie at what are called the two torsion points of the torus. So, I mean, those, if you imagine this being a 2 by 2 grid, these are all the integer coordinates. And now,
so the straight lines on the tetrahedron remain straight lines on that torus?
Right, because the difference is that everything here was multiplied by a 2 by 2 matrix.
Yeah, but this unfolding where you turn your tetrahedron into a torus.
Yeah. Yes. So the point is that every trajectory went to a straight line over here, and now then straight lines are still staying. So it actually is harmless to do that. But now we have these two torsion points, and now this is, I mean, actually these two slides are really something that you could explain to a high school student. We're going to prove this again in a more sophisticated context, but for now this is, what's going on. So passing to the universal cover R2, we see that a trajectory from a vertex to itself, well, because it's a 2 by 2 grid, we're going to be connecting, let's say, the origin without laws of generality to 2q, 2p. But of course, the slope of that is a reducible fraction, and so it has to pass through q, p. Therefore, but at q, p is another vertex of our tetrahedron. Therefore, that vertex is blocking us from returning to the vertex we wanted to start at, and that's the end of the proof for the tetrahedron. In terms of translation surfaces, if anyone's familiar with this, you could say that this is a self-blocking property, but I'm not necessarily going to be mentioning that. And so now we want to deal with the other Platonic solids, and this I need to get fancier. So I have to introduce what a translation surface is, and it's the following. It's just a pair of a Riemann surface with a abelian differential or one form. And I said the genus is greater than or equal to 2. However, we just saw the genus 1 example, and there's no issue with looking at that. And these can be thought of also as polygons on the planes, in the plane with opposite sides identified in a choice of direction. So, I mean, maybe I'll just redraw.
And they're opposite sides?
Right, yeah, let me, that's why I'm going to draw this. Oh, whoops. Okay, so for the octagon, opposite sides are clear. Because every side has a unique opposite side that it's parallel to, and we can glue together. And for this thing, for example, I have to tell you what's actually being identified. And this is also instructive. I'm going to glue 1 to 1, 2 to 2, and then I want to glue opposite sides across in that sense. So, okay. So hopefully this is sufficiently clear for the gluings that I'm doing. And now, if we're standing at any point on this, if we look at the angle around it, okay, 2 pi, there's nothing special. It looks like the plane. However, there's one special point. Let's say I start here, and I want to just go in a circle around this point. Well, that gets glued down here, which goes up here, which goes over there, over there, over there, over there, there, and now I finally close up. And so there's a total angle of 6 pi there. And you would expect this actually right from the beginning, because if the Gauss-Bonnet theorem says that if you have a surface of genus 2 or greater, you can't put a flat curvature everywhere on it. That would contradict it. So you have to have some negative curvature concentrated somewhere, and in this case it's going to sort of essentially be all concentrated at that point where we have angle 6 pi. This nice picture is thanks to Alex Wright, who provided it to me. It's the same thing on the octahedron. As we go around the corners of this, you're going to be traversing every single corner of the octagon, and eventually you're going to get total cone angle 6 pi again. And so both of these are in fact genus 2 surfaces. Okay? Now, I want to, if this slide doesn't make any sense to you, no worries, it won't return again, but I want to say that there's a deeper thing also going on here. So we have this differential can locally be written as f of z dz, where f is some holomorphic function, let's say, and that induces a flat geometry just by fixing a point and then integrating f of z dz along curves going along here. That's how you sweep out your flat geometry. Well, you can do the same thing with kth tensor powers of this, where you take, I shouldn't have used the same function f, but whatever, maybe g of z dz. You take a canonical kth root, and then you integrate that canonical kth root, and that's going to sweep out a flat geometry as well. And I mean, anyone that's studied Teichmüller space is very well familiar with quadratic differentials, and so that's an example of this where k is 2. And you can take what's known as the canonical double covering, and that's going to give you an abelian differential. Okay? So the differential dz to the k, I forgot the tensor there, but this permits edges of the polygon to be identified by any multiple that differs by a multiple of 2 pi over k. So if we think about this for an abelian differential, we're only identifying sides that are parallel with the same direction, and so therefore there is an orientable foliation on this thing. For quadratic differentials, we know that there's a foliation on it, but it's not orientable, and this is because we're identifying 1 and minus 1, the second roots of unity. Well, for the kth differentials, you're now saying that we can't distinguish the kth roots of unity. And so that is making this, actually that's preventing us from even talking about a foliation on such a thing, because the whole thing is folding together. And that's why if you try to draw a foliation on a cube, it just doesn't really work out in any kind of nice way. But we can still pass to this kth root and then get this very nice translation surface. And so for all rational polyhedra, it actually, forget about the Platonic solids and billiard tables, we can just take the least common multiple of all the denominators of the angles and just realize that directly as a k differential. And so, yeah, this is just the observation that, all of these things can be realized as k differentials on a Riemann surface, and unfolding corresponds to taking the canonical kth root, dz to the k. So there is, something else going on here other than just what I think are nice pictures. Okay, so I introduced translation surfaces. I have to introduce a space of them now. So this is a moduli space. It's the strata of translation surfaces. So kappa is going to be a partition of 2g minus 2 for the following reason. If I have an abelian differential, this cone angle, or cone point here, however you want to call it, corresponds to a 0 of the abelian differential. And so locally, this is going to look like, if you choose appropriate coordinates, z squared dz, around this, where the origin is at our cone point. And so that's the only cone point. In genus 2, we have 2 times 2 minus 2, so we're going to look at partitions of 2. Well, this is the trivial partition, so this is actually lying in H2. And you can see that the octagon, well, we also calculated that that had one cone angle of 6 pi. That also lied in H2. If you identify opposite sides of the decagon, for example, you actually get that there's 2 cone points, each with angle 4 pi. And that excess of 2 pi over the 2 pi that you would already expect means that it's going to lie in H11. And so that's the other partition of 2. Okay? And so, yeah, just to summarize that, a 0 of order k has cone angle 2k plus 1 pi. And so a 0 of order 0, a regular point, just has total angle 2 pi. And now this isn't the set of translation surfaces, it's a moduli space, so there's some equivalence. So what is the equivalence? Well, it's conveniently captured in this picture for genus 1. If I identify opposite sides here, I get a torus. So if I mark this segment, cut along it, and then glue this triangle over here, I now get a square. I forget that. All of these pictures are the same. However, I do want to mention that if I rotate the square slightly, that is going to be something different. And that's actually very good for us because I want to consider trajectories. And so if I were identifying everything, in every direction, that would be bad because I wouldn't be able to tell which direction my trajectory was going in. So those are going to be different points, but all of those are going to be the same. Questions? And so the purpose of the unfolding was that it produced a translation surface. And this is going to be a lot easier to study because there's an entire field of translation surfaces with a lot of very powerful theorems. Okay. Another thing that I'm going to be using is something called the GL2R action. So this is a nice observation that if I have this translation surface, which is the one that I drew up here, then if I multiply the vectors on the side of this polygon by some 2 by 2 matrix, why not 2, 1, 0, 1 half, it's going to transform all the vectors like this. But here I have 2 vectors that are being identified. If I multiply 2 parallel vectors with the same length by the same matrix, they're going to turn into 2 other vectors, but those vectors are going to have this and this will still be parallel and they will have the same length and therefore I can identify them. So I'm indeed getting an action on this space of translation surfaces. And I should mention that sometimes, like in this case, if we want to preserve the area of the translation surface, we consider SL2R instead. So let me summarize some key ideas. With this action by GL2R or SL2R, straight line trajectories are being sent to straight line trajectories. And so therefore, I'm not harming any of the dynamics on the surface or any of these trajectories on the surface by multiplying by these 2 by 2 matrices. Understanding the geometry of the moduli space will allow us to understand trajectories on the polyhedron. So the point is we went from the polyhedron to this translation surface, and now I can consider, well, what happens if I start hitting that surface with all the elements of SL2R? That's going to actually tell us something precise about what's going on with the polyhedron, and I'm going to go through that carefully. And it's actually going to be a very elementary instance of renormalization. So I'm not going to mention renormalization again, but there's this concept in dynamics where if you want to study the behavior of a trajectory as time goes to infinity, you can accelerate time and look at longer and longer time scales and then be able to say something about what the dynamics are doing. Here, this is the most primitive version of that, where I'm going to have a trajectory of length 13,000, and now I'm going to make it into a trajectory of length 2, and I can actually see what a trajectory of length 2 looks like. So this is going to be, here, we have this diagonal matrix coming from something called the Teichmüller geodesic flow. But the point is that the e to the minus t, that's going to change this larger length trajectory into a shorter length one on a deformed surface. Okay. So let's talk about the torus now. So what happens if we act on the torus by SL2R? So this is going to give us some set, but then the observation is the following. If I take the torus and I multiply this by 1, 1, 0, 1, it's going to shear it horizontally. If I multiply by 1, 0, 1, 1, it's going to shear it vertically. And so in both of these cases, I'm going to get the torus back. However, this group, or these two matrices, they generate the subgroup SL2Z. And so SL2Z is a lattice in SL2R. So if we just mod out, we're going to get that the orbit of the torus is closed. And yeah, SL2Z is called the Vich group of the torus. And after forgetting the differential on the torus, we actually just get the modular curve in the upper half plane. And that's going to be called the Teichmüller curve of the torus. So this is a, I mean, for the torus, it's a very familiar picture.
So what's the modular curve?
Oh, yeah. Sure, no problem. Yeah, please feel free to stop me at any point. So it's this region in the upper half plane where this is glued to this and this to that. And this is given by doing SL2R mod SL2Z. So yeah, sorry. And yeah, please, I mean, anyone, if you have any more questions, stop me as I go along. So, arithmetic Teichmüller curves. Here I'm saying, well, let's say we take a finite cover of the torus. Okay, if I take a finite cover of this torus and I, respect the differential on it, then really what I'm doing is I'm just gluing a bunch of tori together. And so maybe I want to consider, again, let's go back to this picture, but now I'm actually going to say that, I care about these lengths. So this is the same as this, except here I'm saying this is really glued out of 3 squares. This is a degree 3 cover of the torus. And because the GL2R action is going to commute with covering maps, any finite cover of the torus is also going to have a closed orbit. And so, yeah, a degree d ramified cover of the torus is going to be regarded as gluing the d squares together. And so, sorry, that's a key word I should have mentioned. I do want a ramified cover. So it's going to be ramified over this point. If I just considered degree d unramified covers, I'd be getting the torus over and over again. So that's certainly key. The Vich group of the cover is going to be a finite index subgroup of the Vich group of the base surface. So that's also true. And then, of course, this is also nice because now we're talking about finite index subgroups of SL2Z, which are well studied. And there's algorithms to study them.
I don't understand
Yes.
what you mean by
Sure.
closed orbit.
Yes.
It's the orbit for the action of what group on what space, and what do you mean by it's closed?
Yeah. So, yeah, good question. So if I had, this wasn't as, it's sort of clear that things have to go the way they did for the torus, because the Teichmüller space of the torus can be regarded as the upper half plane. The moduli space can be regarded as this modular curve. And so SL2R is just giving you everything. So of course, the closure of this thing had to line up with the whole, with everything there. However, once you go to the modular, the closure of the SL2R orbit. So each point in here corresponds to, some torus. So this is maybe this torus, this is the hexagon. If you identify opposite sides, you get a torus. And so each one of these points parametrizes, this is a space of tori. And I'm saying if you act on this by SL2R, you're going to get to every other point in this moduli space.
Oh, I see.
So closure is trivial to say there. However,
So the SL2R orbit of the torus in
Yes.
the moduli space.
Yes.
is closed.
yes.
Okay.
And that's not a trivial statement once you get to H2. Once you're in genus 2, the dimensions, so the dimension of the moduli space in H2, so the complex dimension is going to be 3g minus 3 plus the g-dimensional bundle of abelian differentials. So that's 4g minus 3. So in genus 2, you get 8 minus 5, right? And the point is that you have some 5-dimensional space. SL2R has dimension much smaller than that, so you don't necessarily expect a closed orbit. Nevertheless, the covers of these tori are going to be closed. And so they have the smallest dimension possible. Yeah, yeah. Thank you for stopping me there. And so finally, one thing that's, if you have a closed orbit, then any point in the closed orbit is called a Teichmüller curve. Any point in the Teichmüller curve corresponds to something called a Veitch surface. And Veitch surfaces have very special dynamics on the surface. When you're on this translation surface, if the surface is a Veitch surface, every trajectory is either a closed trajectory, and then closed trajectories all parallel to each other, or the trajectory is uniquely ergodic. We're not going to be using that. I said that because that's his theorem, but I mean, you could just reinterpret that as saying it's a dense orbit on the Veitch surface. Okay.
So Veitch surface is a point on the Teichmüller curve of which?
Yes. So once you're on a Teichmüller curve, then any point in it is a Veitch surface.
So you start. So what's the surface you start with that you're looking at?
I mean, yeah. I mean, well, whatever surface you start at, if it generates a Teichmüller curve, then it's a Veitch surface. Otherwise, it's not.
But whatever surface I start with, can't I just look at, it's the SL2R action on it?
Yeah.
So I get a Teichmüller curve from any curve.
Not from any curve. If these things aren't lining up properly, so let's say that this has length 1, 1, 1. So let's say I have 2 unit squares here, but this, I'm just going to say has length E on that side. That's not going to generate a Teichmüller curve. I mean, I don't expect you to see why, I don't know if that's true, but this would be an example of something where the orbit of this is actually going to be dense in H2. And so the diagonal action was proved by Maser and independently Veitch that it's ergodic on the space, and so yeah, you're going to have a dense orbit there. So then the closure is just the entire giant space. But if you're dealing with these covers of tori or some other very special things, it turns out that you're going to have a closed orbit. And so, I mean, here you're getting the closure of some 5-dimensional space. Here you're getting it's this small, maybe one or two complex dimensional space, depending on how you count it. Does that make some more sense?
Well, I guess I don't know what's the definition of a Teichmüller curve.
Yeah.
Oh yeah, it just means that it has a closed orbit. We can just define it by that. So there's a lattice subgroup that, when acting on this, fixes it. There's a lattice subgroup of SL2R, and therefore that's what's giving you the closed orbit. So the definition, I should say, is it's a theorem of Smiley that these things all align, but so we can just take the definition as it's always stated, is that there's a lattice subgroup of SL2R that fixes this in moduli space.
Okay.
So you multiply by some element of this lattice, you cut and reglue, and you get right back to where you started. Yep. Okay. Better?
Yeah.
Good. Okay. So periodic trajectories on translation surfaces. So one thing let's return to our Platonic solids now that we've talked about some theory. Every vertex on our Platonic solid is actually going to lift to a unique zero of this corresponding translation surface. So you can imagine, I mean, here I have my net, I unfold it, I unfold it, I unfold it, I unfold it. Okay, I get back to where I started. And now I have one of my corners in the net for the vertex of the Platonic solid. And now I start going around. It turns out that on the unfolded net, of course I have to get a zero of an abelian differential there, but I'm only going to see 1 0 lying above that point. So there's a unique zero to which every vertex unfolds. Okay? I mean, you just need to work this out. I don't expect you to just see this.
So depending on the angles, you have some differential to the power something, and
Yep.
you're taking its kth root, and that's
Mhm.
that's your translation surface.
Yes, exactly. Some terminology, a saddle.
Can you tell me that? I'm not that familiar with these things. So can you take an example? So like.
Oh yeah, I'm going to show lots of pictures of this.
Okay.
Yeah, absolutely. I'm going to show pictures of every one of them, basically. Yeah, so let me, starting with the torus, but just to introduce some more terminology. So a saddle connection is a trajectory between two zeros, just to give a name to that. And the two zeros don't necessarily need to be distinct. And so what this says is that since every vertex is lifting to a unique zero, if I want to study trajectories from a vertex to itself, it suffices to study saddle connections from a zero to itself on the translation surface. Okay. I guess, sorry, a little bit more theory before I start drawing all the pictures. So Teichmüller curves, they also have an additional structure that's extremely nice. They're algebraic and they're non-compact. So just like this modular curve here, which has a cusp going out to infinity, Teichmüller curves always have cusps, but there are always at most finitely many of them. And so now, let's see what happens. For these cusps, remember, the Teichmüller curve is a parameter space for our translation surface. So anytime we take a point, even if it's all the way up here, this is going to correspond to some, in this case, a torus. So what does that torus look like? So this is easy to describe. It's going to look, the torus is going to look something like this all the way up here. There's going to be a very, very long, thin cylinder. And this is true for all Teichmüller curves. All the cusps correspond to having really short trajectories on them, but that are all getting pinched, effectively, because the modulus of these cylinders is going to infinity. Okay, so modulus height over width. And what's the upshot of this? Well, here's where I'm saying that if we understand the geometry of these Teichmüller curves, we're going to understand the Platonic solids, because these closed trajectory, anytime you have a closed trajectory, you can use the diagonal matrix to contract it to length less than epsilon and end up in one of these cusps. So therefore, any of the infinitely many periodic trajectories we might have all end up going into one of these cusps. And if you can understand what goes on in each of the finitely many cusps, then you've solved the problem. And so now the whole point of this is reducing it from the infinite problem to the finite. Okay, so now let's go back to the tetrahedron, because we're talking about the torus. So before we were looking at all the integer, lattice points in the plane, let's do something much simpler. This Teichmüller curve of the torus has a single cusp. Therefore, all we have to do is look at a single direction on the torus and prove the theorem for that. Right, so Teichmüller curve is one cusp. So if I'm going to choose a periodic trajectory, choose the horizontal. And so here's my torus. I'm going to draw in the two torsion points. And now I need to check that if I start at any vertex and I go horizontally, I have to hit another vertex. Well, of course. Just look at it. I mean, here I have to go through that one, here I have to go through that one, here I have to go through that one. There's just no way to go horizontally. But that actually suffices to prove the entire theorem for the tetrahedron, because every horizontal trajectory can be transformed into every other periodic trajectory by an element of SL2Z. So I've now reduced it to checking one thing. And now we have this whole theory of translation surfaces. Let's go and use a computer to prove the other ones. So This is Sage, which is an open source program. I mean, yeah, this is just available online. Pat Hooper is developing some new stuff for it, so he's able to do some really cool things now. Let me just write that down. And so there's two packages. There's the Surface Dynamics package. Let me actually get this correct. Yes, underscore. And there's also a new one being developed by Pat Hooper and Vincent Delacroix called Flat Surf. Okay. So Flat Surf can now do things like this. Here's a trajectory on the dodecahedron. We can rotate this around so I can everyone see. So this is the dodecahedron that I just passed out. And so now let's go to the tetrahedron and just see an example of how this works. Right. So for the tetrahedron, you can glue it together from 4 squares. And so the way it gets recorded in here, so 1, 2, 3, 4, is just through permutations. So horizontally, we're going to see square 1, square 2, and then close, so call that a 2-cycle 1, 2. And then we're going to see 3, 4, that's another 2-cycle. Vertically, we're going to see 1, 3, and 2, 4. So that's what this is recording. I don't know if that's too small for anyone to see. I apologize. And then this is able to find the Veitch group, it's able to find the index, and it's able to find the number of cusps. And so, of course, for the tetrahedron, it's a index 1 subgroup in SL2Z. It is SL2Z. And it tells you all of that. And so therefore, and it doesn't know about marked points, so it says that it's in genus 1 with 1 marked point. But, well, we know otherwise. But then that isn't an issue for any of the others. What's interesting is then it's not clear why the octahedron is a square-tiled surface until you make the following observation. Where is it? Yeah. Let's go back. There we go. So, notice for the octahedron, so of course it's glued together by triangles, but in spite of the unfolding, there's only 2 kinds of triangles that occur. Either the base is on the bottom or the base is on the top. And anytime you have a triangle where the base is on the bottom, it's glued next to it to a triangle with the base on the top. That's a parallelogram. And a parallelogram can be sheared into a square. Maybe stretched a bit. And so then, because all of these have to occur in pairs, this is in fact square-tiled. So for that reason, you can then work out what the permutations are. It's, you know, an afternoon of work to do it for each of these Platonic solids. But, sorry, let me just get back to where I was. Yeah. And turns out that the resulting translation surface lies in genus 4 with 6 simple zeros. It's an index 4 subgroup of SL2Z. And there's 2 cusps, which means I need to check 2 directions. And now this comes...
So is there an easy way to figure out the genus, for example?
For the Platonic solids, yes. Because all the vertices are the same, you just figure out one of them, you figure out how many you have, and then you just...
So for example, for the octahedron,
yeah.
You said you get a genus 4 surface?
Right. So you have 6 simple zeros. So a corner of the octahedron meets 4 triangles. Okay. And so 4 triangles, that's angle, right? So pi over 3 times 4, so 4 pi over 3.
Pi over 6?
Wait, why?
Oh, pi over 3. No.
Pi over 3, okay.
Sorry.
Sure. And then, so yeah, so I know, long day. Yeah. So 4 pi over 3, and now you have 3 copies of those because there's only one thing above. Yeah, so it's a cubic differential actually, and so I mentioned that you only have when you work it out, that unfolds to the smallest thing to multiply it by. Yeah, so the smallest number you can multiply it by to get a multiple of 2 pi is 3, and then that gives you total angle of 4 pi. So for an abelian differential, angle of 4 pi means that you have an excess of 2 pi, which is 1, so that's a simple 0. And then you do that for all 6 vertices, and that gives you 6 simple zeros. But 6 simple zeros, if you solve 2g minus 2 equals 6, g is 4. Yeah, so,
Thanks.
yeah, no problem. And then you can do this for all the other ones. And so, yeah, number of cusps is 2. And so, maybe I'll just go through this proof here. All you need to do is look at the horizontal and the vertical, and you'll see that there's 2 different decompositions of periodic decompositions just by comparing cylinder circumferences. In the horizontal direction, looking at this thing, every cylinder has circumference 2. In the vertical, it turns out it's 3. And then it's this game of saying, well, all the vertices are colored all the zeros are colored by specific colors. And so then you can't get from purple to purple in the horizontal one without going through blue. And so it just becomes this game. And vertically, I can't get from purple to purple without going through these 2. So that ends up being the proof. It's just comparing colors at that point. You could then do the same thing for the octahedron, which is in genus 9. And actually, it's computing this on the fly right now. Oh, sorry. No, that's not the octahedron. Sorry, the cube, which is in genus 9, glued from 24 squares. It has 3 cusps. And because it's 3 cusps, you can just look by hand, which is what I did, and said, OK, I noticed that I have 3 different periodic directions. Therefore, that's sufficient. End of proof. And then you compare colors again. And the icosahedron is a lot more work. You end up with 60 squares. But again, there's only 3 cusps. And so you can compare colors. So that is effectively a complete computer-assisted proof for everything except for the dodecahedron. And so, I guess, how much time do I have?
You probably have until 3 past, right?
OK. So let me at least say what I can here. So it turns out that for the dodecahedron, you don't get a square tile surface anymore. This doesn't cover the torus. And any kind of nice translation surface way. And so what happens is, I need to just recall something discovered by Veitch. So when Veitch first discovered what have come to be known as Veitch surfaces, he called them lattice surfaces. One of the first examples he presented was something called the double pentagon, which is exactly this. Sorry, it's a little faint. So 2 pentagons, and every side has a unique side that's parallel to it, and we glue them together. And this gives you a genus 2 surface in H2 again. Its Veitch group is not a subgroup of SL2Z. Of course, it's a subgroup of SL2R. And it's something known as the Hecke triangle group, the 2-5 infinity group. And in this picture is 2 generators, rotation by pi over 5, and shearing by 1, 2 cotangent pi over 10, 0, 1. Okay? And it turns out that if you act on those, you can actually glue this. The rotation is not surprising, but the shearing is often called the modulus miracle, because the moduli of the 2 horizontal cylinders end up perfectly lining up that one matrix can shear both of them simultaneously. And the Teichmüller curve of the double pentagon, it's very nice. This is a good geometry. There's a single cusp. Turns out that the net of the dodecahedron, this is the hardest one to deal with. It ends up being a 10 differential. OK, so the dodecahedron is glued together from 12 pentagons. It's a 10 differential, which means you need to take 10 rotated copies of it, and you end up with 120 pentagons. this is kind of a nightmare. And also the reason why I would speculate that no one was really able to touch this before. It's really complicated. It's a genus 81 surface. I really don't encounter those. I've never encountered one of those before. I never really wanted to work with one before unless I had a really good reason, and I think this is good enough reason. And every vertex lifts to a unique point with cone angle 18 pi. So this is actually lying in a stratum with 20 zeros of order 8 in genus 81. Again, not something I've ever thought about before. Nevertheless, it covers a double pentagon, and therefore it's a Veitch surface. But now, we don't have sort of publicly available software to deal with this. So, but the Veitch group of this unfolded dodecahedron, it's a finite index subgroup of that triangle group that I mentioned before. But it's not something you ever want to handle by hand. It's an index 2106 subgroup. I believe that because it's a degree 60 cover, it could have been 60 factorial. So from that perspective, this is so much better. But to deal with 2106 coset representatives is something you have to do with a computer. And this was computed using software developed by Miriam Pfister in actually her master's thesis. And then she wrote her PhD thesis on this. And then Pat Hooper, now with his flat surface program, he was able to at least confirm this number. And now we're working on trying to do something that might be able to sort of rigorously say that. Nevertheless, Miriam was able to provide us with a full list of coset representatives. Yeah, actually, we don't need this last count. It turns out R is in the Veitch group of the unfolded dodecahedron, but that's not, I'm not going to use that right now. Okay, so how do we reduce this? Because now, what's the game here? For the other Platonic solids, the trajectory from the vertex to itself didn't exist. Whereas for the dodecahedron, because this is a Veitch surface, there's going to be infinitely many trajectories from a vertex to itself. So how do we, in some sense, classify them? Well, we'd like to put them into equivalence classes. So the first equivalence class you'd want to put them into is maybe action by the Veitch group of this, giant 120 pentagon thing. And that's actually not what you're going to want to do in the end. There's duplicates there. But the point is that if you imagine this picture, sure, we have a degree 60 cover lying over this double pentagon, but at the level of the Teichmüller curve, we have some point in the Teichmüller curve of the double pentagon, whatever this looks like. And then we have some really complicated thing. Incidentally, Miriam's program finds that there's 350 something cusps. So just going through cusp is also not going to work. And in the fiber over this point, we have 2,106 points. To get between these points, we just multiply by the coset representatives. And so what we're going to do is just multiply by the coset representatives, look for one of these two saddle connections, because every horizontal saddle connection can be reduced to one of these two. And then once we find something, we can invert the action by that coset representative and go back up to the top. And so, yeah, that's exactly what the game is. Yeah. So sorry I had to go through that fairly quickly. But that's going to allow us to build our full list. At this point, don't put any weight on the number I'm about to say. But we found there seem to be 119 different equivalence classes of these trajectories, but that could change as we debug our program. So, yeah, I mean, this is just summarizing what I said here about starting up here, going back down, and then going back up.
So how many do you know that there are that are distinct?
Oh, so I can do better than that. So Pat is really amazing at drawing these things. So this is all 119. And they all start looking different. Now, we haven't and actually you can see, here's the vertex right here where they're coming in exactly to that vertex and, oh, no, I take that back. That's not clear. I don't know, I forget exactly where the vertex is that he chose. But yeah, I mean, this is a 119-page PDF that we generated of just going through all of these things. And it was sort of just very gratifying to see how each of these things. Huh?
Is it this one where there's always...
It could be, yeah. Yeah. Yeah, because you see that.
Intersections inside the net, what do they correspond to?
Yeah, so I mean, the thing is, unlike for abelian and quadratic differentials, for the 10 differential, there's no foliation. And so these trajectories do have to intersect if they get long enough at some point. But yeah, I mean, as far as what the significance of the intersection point is, I have no idea. Yeah, it's a good question.
So is it
Yeah.
obvious that there should be finitely many types of these? Or?
Well, yeah, there's finitely many cusps of the Teichmüller curve. So everything's going to be at least one of those times an element of the Veitch group. But actually, then the other annoying thing is that the sharing that's an element of the Veitch group for the double pentagon is not an element of the Veitch group for the big cover upstairs. You need to take like t to the 15th or something to get an element there. However, if I take a horizontal vector and multiply and shear it, it's still a horizontal vector. So these are two different coset representatives, and yet they're going to give the same trajectory from a vertex to itself. So on the original list, there were 177, and we noticed there were a whole bunch of duplicate trajectories. It's coming from that phenomenon. So then you need to mod out by another group to get your relations. But yeah, I mean, I'll leave this up here, but yeah, that's it. So thank you.
Any other questions?
So what, do you know what the longest one is?
I mean, so one thing that Pat's trying to program now is he's trying to program Dirichlet domains into the flat surface thing, because that would allow us to find the shortest trajectory within each equivalence class. And we don't know what the shortest in each equivalence class is right now. The longest trajectory, just blindly doing the whole coset thing, ends up being 18,000 something. And I mean, in the completely uninformative picture, it looks like that. So yeah, I mean, maybe there's a shorter one in there, but we don't know right now. Right. Yeah.
All right, let's thank David.